3 students, this is Chris Wicks. I'm going to be doing the vector projection problem of the man rappelling down the face of a mountain. I remember having some trouble grasping the concepts to this initially, and admittedly it's still a little slippery, but it was really helpful to go back and review this problem, and hopefully my presentation will be helpful for you as well. The problem states that a 150-pound man is rappelling down the face of a mountain. If the angle of the rope makes with the vertical is 20 degrees, determine the components of the force of gravity on his weight acting along the rope and perpendicular to the rope against the mountainside. Provide a labeled diagram, state the force and rope vectors clearly, and give an interpretation in words of the magnitudes rounded to the nearest tenth of a unit of these two vector components. And just a heads up, I apologize in advance for any shaky camera work. My usual assistant is out of town for the week. So first of all, just draw a diagram. Shows the y-axis represents our very straight mountain. This is our little guy right here. We have the rope, and this F right here represents the force of gravity acting on the weight of the man. The rope, this isn't quite to scale this vector here. What we're going to see is that we actually need a unit vector on which to project F. Now, again, the problem asks to determine the components of the force of gravity on his weight acting along the rope and perpendicular to the rope. So that should give you a heads up that we're going to be doing vector projection. So first of all, the component of the force of gravity acting along the rope will be the projection of F onto R. But before we get to that, we just need to state our vectors real quick. These are pretty much given to us by the problem. F is 0 in the x direction and negative 150 in the y direction. That should make pretty good sense. Gravity, it acts down, and that's about it. R is cosine of 70 degrees, sine of 70 degrees. That's a little trickier to get. Remember, we're 20 degrees with the vertical, so the angle R makes here with the x-axis is going to be 70 degrees, and that is how we're going to be measuring R, not with the angle it makes against the y-axis, because that's how we measure our vectors. Anyhow, moving on. While I change scenes, remember that the projection of vector u onto vector v is the dot product of the two vectors divided by the magnitude of the vector being projected onto quantity squared times the magnitude, or times the actual value of the vector being projected onto. So we get two scalars, the quotient of two scalars here, multiplied by a vector quantity, and we end up with a vector, which is the projection of u, the vector component of u, acting along in the direction of vector v. So we want the projection of F onto R. Sorry, it's hard to see that that is an R, but that is indeed an R. The projection of F onto R, the projection of the man's weight acting along the rope, in other words. So remember, these are the values of our force and our unit direction vector, R. F dot R is 0 times cosine of 70 degrees. We just take the product of the I terms and add them with the product of the j terms, and that comes out to be negative 150 sine of 70 degrees. And then the magnitude of R is just 1. It ends up being cosine squared of 70 plus sine squared 70, which is, as you remember, cos squared of x plus sine squared x equals 1. The square root of 1 is 1. And as you can see, R is indeed a unit vector. Moving along, projection of R onto F then is we take their dot product divided by the magnitude of R squared, multiplied by the vector R, and we end up with negative 150 sine 70 cos 70 for our I component, and negative 150 sine squared 70 for our j component. We can simplify that a little bit. Remember, sine x cos x equals 1/2 sine of 2x. So divide 150 by 2, you get 75 sine of 140, negative 150 sine squared 70 for our J component. And that is our projection of F onto R. The projection of the man's force, the man's weight vector, force of gravity on the man's weight, projected along the rope. Now, the next thing the problem asks us to find is, the problem asks us to find first the components of the force of gravity acting along the rope. That's what we just found, and then also perpendicular to the rope. In other words, against the mountainside. So to find that, remember, here I just replaced it with our actual vector names that we're using. F perpendicular is equal to the original vector F minus the projection of F on R. Now, this should make pretty good sense. I actually, to illustrate that, redrew the diagram, moved our vectors around a little bit. Remember, we can move our vectors anywhere on the plane, and they're still considered to be the same vector. But this sort of illustrates nicely what is going on here. So we have our unit vector R that we're projecting onto. And then we take F, this is the force of gravity on the man's weight, and the projection along the rope is here, and then it should make good sense that F minus the projection of F onto R is going to give us F perpendicular here, because what we're basically doing is splitting the components of F into two vectors that are normal to each other. Now, from here, we just do the math. It's pretty straightforward. We take F, projection of F on R. F perp is then the difference of those two. F minus the projection of F on R equals 75 sine of 140, and negative 150 times 1 minus sine squared 70. 1 minus sine squared 70 simplifies to cosine squared 70. So our F perp is 75 sine of 140 in the I component, and negative 150 cosine squared 70 for our J component. Finally, the problem asks us to interpret our findings. It says, give an interpretation in words of the magnitudes rounded to the nearest tenth of a unit of these two vector components. So first, let's just find the magnitudes. Pretty straightforward math. We don't really need to go into all the calculations. We can just take the magnitude of the projection of F onto R is just the square root of the squared sums of its vector components. I think that made sense. Take the two components, square each of them, and add them together, take the square root. We can just plug that into our calculator, and we get 141.0 pounds, rounded off, about 141 pounds. Same thing with F perp is about 51.3 pounds. Now, that should make pretty good sense. Recall, with our initial drawing, we have the man's force acting down, and it looks like most of his, if you just look at it, it looks like most of his weight is going to be directed along the rope. So our results here make pretty good sense. Some of it gets directed towards the mountain, most of it goes down the rope. And interestingly enough, note here that they don't necessarily add up to the same magnitude as his weight vector. Now, interpreting this, the projection of F on R, the projection of F on R represents the component of the man's weight vector that's being directed along his rope. His rope needs to be able to supply an equal, hopefully much greater resistive force. And the magnitude of F perp, 51.3 pounds, represents the component of the man's weight vector that is being directed perpendicular to the rope towards the surface of the mountain. And we can assume that that's not going to be sufficient to uproot the mountain. Anyhow, I hope this has been helpful and informative, and good luck on finals, everybody. Have a good night. Bye.